Hi. So today I'm going to go through this paper, vector-based navigation using grid-like representation in artificial agents. And this is work done by Andrea Bonino, Cosmo Perez, and many others at DeepMind, I believe. So what this paper is about mainly is how you can train a neural network, namely a recurrent neural network, in a specific way to perform a specific task. So in a reinforcement learning scenario, in which this grid-like activation function or grid-like patterns arise in the activation functions of this artificial neural network, much like the same grid-like patterns arise in the neurons or of mammals in the form of this grid-like grid cells. And so let's get into it. So first, I'm going to give a little bit of an introduction of what place cells and grid cells are, and also head direction cells. So place cells are the easiest one, and these are cells that each cell or each neuron fires only when the agent, in this case this rat here, finds itself at a specific location. So for each location, there's a different neuron that fires only for that location. You can see here there's like a neuron for each of the colors. They represent a neuron. And that neuron fires only when you're in the vicinity of a specific location, any of the points or any of this point, the location along this path here. So if you were to imagine this place cells in a square arena, that would only fires around a specific location here. Then you could have another one, and only fires when you're around that one, as opposed to grid cells, which they fire at a fixed distance. So you could have a cell that fires every time that the agent goes through the 3 meters or covers 3 meters, that cell fire in different direction. They kind of space out evenly over the whole the whole space. So it gives an idea. It gives the agent an idea of how much space did it cover, and this can be a different. So there are many of these grid cells in the brain of mammals, has been proven, and these are at different scale. So you might have one in which the distance between each of the activation of each of the grid cells, it's like only 3 meters, and then another one is like 3 centimeters or 1 centimeter. Another one is like a much larger scale. So you have all these scales, and together they give the agent a very good representation of where it's at and how much space did you go through in general. So these are the patterns that we want to see arise in this paper in an artificial network. So let's have a look at how this is done. First of all, they to achieve this, they have an agent moving through in an arena. So this is just a general arena in which an agent, which is kind of a motor control model, which is similar to a rodent. To make this kind of a artificial or a digital analogy to the same experiment done in mammals, and that it can reproduce. And he moves around either with a specific reinforcement learning policy or by taking just random actions. And the velocity that the agent is so with which the agent is moving are given to as an input to LSTM. There's a velocity there given to which is that some noise is added, so that are kind of they mimic the kind of information that are available to a rat, in which it doesn't exactly know the value of the velocity, but it just has a general idea that when it moves to the left, there's an acceleration to the left, kind of like an accelerometer, I would guess. And also to the LSTM, the initial hidden states and the cell state are given, so they're initialized as a linear combination of the start position. We're going to see in a moment in more detail. And then there's an output of the LSTM. So the hidden state of the LSTM, which is its output, is passed to a linear layer, and then the output of the linear layer are given to a predictor that predicts the place cell. So a cell that activates only when you're around it. You're in its immediate vicinity, and the head direction cell. So we haven't covered head direction cell. Head direction cell is the same principle as grid cells, as place cells, but they fire only when the agent is facing a particular direction. Um, and so you have these two things, and these two things are the thing that you're trying to predict. We're going to look at the activation of this kind of pattern in the linear layer. So we want it to arise in the linear layer. And going into the details here, the place cells they want to predict here are expressed as a posterior probability of a Gaussian, given that we know given a specific position. So the Gaussian is centered each at some position here. So there's going to be a Gaussian place at this position, one at this position, one at this position, and one at this position. Let's say there are 4. So for each 4 of our Gaussians, we're going to calculate the posterior distribution of the Gaussian given the current position of the agent. And that's going to kind of give us, if we are like thinking kind of in probability terms, it will give us kind of what is the likelihood that this point in space was gotten to by sampling from this particular distribution. So if it's very close to that distribution intuitively, the likelihood of it being a sample from that distribution is going to be much higher. And if it's very far away, let's say the point is over here, it's going to be much less likely than it was sampled from that distribution. So it's kind of like a measure of the vicinity to that particular point. To that particular place cell. So each of these, this is kind of a way to represent a place cell. With these Gaussians, each of which it is a cell. So each of which it is a place cell. And the same kind of reasoning is applied to the head direction cells. Only these mixture of Gaussians are distributed around the agent instead of like kind of separate in space, kind of evenly spaced over the whole arena. They are evenly spaced around the agent, so you can express kind of the direction in which the agent is facing as a mixture of these Gaussians. And then the last function is like the cross entropy between the true place cell, or the true activation of the place cell. So remember, there's a probability, so they kind of go between 0 and 1. And like the one predicted by this output layer of the LSD, so by this grid cell network, let's call it. So that's how it's learned. And so here you see the activation function. So sorry, the initial state is like a linear combination of the cell state of the start, so of the beginning state, initial state. It's a linear combination of place cell and head direction cells at the beginning of the trajectory. These are the initial state of the initial hidden state and initial cell state of the LSTM. And here they have so the input are the velocity and the angular velocity, the sine and cosine of the angular velocity. And also quite important is they're going to see these kind of patterns arise in the activation function. So they look for this pattern of grid cell, like the grids that are like grid cells, in the activation of this layer here, this linear layer. And these, they say in the paper, don't arise unless they use some kind of regularization on this layer. And they're going to use a dropout regularization, which they say is analogous to what happens in the brain. At some time you have some like neurons firing, and sometimes because maybe there's some noise in a network, they don't fire at all. So you have to have kind of redundancy in the brain, have multiple neurons doing the same task, performing the same function, so that one of them doesn't work, you have another one as a backup, and so forth. So by kind of crucially, the behavior of the activation function here that they want to see, that we're going to see in 1 second, doesn't arise unless they use this kind of dropout, and it doesn't really explain why that is. Like they just say that it's analogous to how the brain works somehow, and but they don't really explain why that is, or in kind of in this in the artificial neural network. So these are the patterns. You can see that they really much look like the things that we saw at the beginning. This one, the kind of the biological counterpart of the grid cells, and this is the one that arise in the recurrent neural network when you train it in this way. And this is an autocorrelogram, and you can see that they are a different. And this is just when do they activate? So each one of these is a specific neuron. And this shows when does this neuron, and this is like a map of the arena, and so like this kind of the red color, what it means is this neuron activates much more often when, or it has a tendency to activate to be active when we are around this area in the arena, and also this area, right, and all these areas. And then like you can see that we have the same kind of thing with different neurons have different scale, right? This one is much more frequent. The grid is much more less coarse than this neuron. And here you can see like how the activation of this neuron correlates with the agent facing a particular direction. So you can see that in this last one, the agent is not, so the activation doesn't really correlate with any position in space, really, but it correlates a lot with the specific position, orientation of the agent that is facing. So that is kind of a head direction cell. So it's the artificial analogous of a head direction cell, and this one is like a border cell. So this one gets activated as also another kind of cell, together with head direction cell and grid cells and place cells, that gets activated only when you are like going against an obstacle, right? So it says that we cannot pass through that particular point in space. Okay, so now that they've proven that this kind of pattern arises when training in this way, they want to incorporate. So what we've been talking about is this one. This is the grid network. They incorporate this into a policy, a reinforcement learning policy, where the vector. So before this one is, so the one that exhibits this kind of pattern before it is passed to a linear layer to predict the place cells and the head direction cells. This is passed to the agent, together with the same kind of vector, but when the agent, this is the same kind of vector, but when the agent gets to the goal, they're going to take that vector. So the agent has to get to a goal in this experiment. They're going to take that vector and concatenate it together with its present vector of the grid cell. I know it's a little confusing. So together with that, it's going to get the previous action and the reward for that step, and also it's going to get kind of the embedding of CNN, convolutional neural network, where that is given as an input the image that the agent is seeing at this particular moment, and the output is going to be a distribution of our actions, a discrete distribution of our action, and there's going to be a critic that's going to output the value for this action state pair, and also to make this more like the real experiment, or a real rat would get this information. And they train a model that's given an image, a convolutional neural network is asked to predict the cells, the place cells and the head direction cell. So he has to perform a prediction, and he's trained the same way that the grid network is trained. And this thing is given to its prediction of Y and Z, so the place cell and the head direction cell is given to the grid network. And this is because if it was only to integrate this noisy velocity, it would drift. So the error would become bigger and bigger because there's no way for it to correct. But given that it gets this kind of estimate of its of the place cell, it can correct for it. And like in a real rodent, it doesn't get to, they want to make it more realistic, so it doesn't get this information all the time. It gets it 5% of the time. So it's kind of, I don't know, as if the agent only looks up at its surrounding to kind of understand where it is only a certain amount of certain percentage of the time. And so that is kind of the network. So how they integrate it with a reinforcement learning network. And what they do here is they have a kind of a artificial counterpart to this experiment here. This is the water maze, or the water navigation test. And what they do here is they place a rat into this pool, and the rat is asked, I'm not reading, but he's going to have an incentive to find a platform which he can stand, and he's going to be placed every time at a different point in this pool. So the first time he's going to explore around, and it finds a platform. When put in the second initial position, if it encodes the place it has been, its path in the correct way, it's going to know where it was before, what the platform was. And even though it is initialized in a different position, it can kind of figure out where to go without kind of following the same path, but just going in a straight line to the platform. And in the experiment, the original experiment, there's also a landmark which enables kind of the agent to know where it's at, to have like some visual cue that gives him a possibility of self-locating. And so what happens in this experiment is, like in this digital or artificial version of this experiment, you have this architecture that I've been describing, where, by the way, each of these things is like only this thing. The final agent is trained on this. Is trained basically. Each one of these components is trained separately, right? Yeah. And what it enables, so this grid cell representation that it has coming from the grid network enables the agent to have like, so here you see how what is amount to. Like you have different grid cells at different scales, and you have one for the goal and one for the present for the current position, right? And what the agent can do is kind of perform vector calculation that allows him to know how far he currently is from the goal position and which direction the goal position is. And this is a calculation that once these codes are given, are performed by the policy LSTM. And so you can see that once, so at first it doesn't have, so this part, the goal grid code is not available at the beginning. But so you see that at the beginning the agent is from the start position S is starting and is wandering around and gets to the goal. And once he gets to the goal, the state of that, so this thing here, the activation of this layer here of G are given, is what is given here as a goal grid code, or here as G star. And what it allows it to do is this kind of vector calculation, okay? So you can see that once it finds it, then it doesn't matter where it is initialized. It just goes more or less in a straight line to the goal. And then they also do the experiment when they kind of substitute this goal grid code, not with the place where the platform is, where the agent should go, but with some random other location in the arena, and the agent starts circling around because it does have access to a reward. So much like the real version, the agent, the rat, knows when it gets the reward, or when it gets to the invisible platform, because it can feel it, right? In the same way here, there is like a vector that is given where he remembers the platform to be, but there's no platform. He gets no reward from the environment, and he sees no reward. So it starts circling around, much in the same way that, and this is a real version of the experiment. If they remove the platform once they found it, it will kind of circle around. So they have all these analogies between the real version of the experiment and this artificial created version of the experiment. So they also have like a comparison with another agent, and this is the place cell agent. So whereas this one has this grid cell, has access to the grid cells, and he compares the vector of the grid cells, this other agent, the place cell agent, has the ground truth of the cell agent, of the place cell. Sorry, both of the goal and the current position, and everything else is basically the same as the other one. They both have access to the image input, visual input, and all the rest. And then there's like this other agent that we're going to see in our experiment, where the agent does not have any access to any kind of position information, only has access to the visual information. So this is like the normal actor-critic network that we're going to see. And here you see that it's superior, like the grid cell agent is superior, although kind of the same kind of information is given also in the place cell agent, but the fact that it encodes the information about its position in this way, this grid cell way, allows him to perform this vector calculation, or to perform vector-based kind of navigation. Okay. Next, they have other experiments where the environment is a little bit more difficult. Here they have the kind of still the same principle, where the agent has to find a goal and then is moved somewhere else and has to go to the same goal. But here in this kind of maze-like environment, and here like the agent is trained first in a kind of environment, and then is tested on a different kind of environment, a different structure of the environment, different design of the environment that are procedurally created. And the test time, normally the maze is bigger than the one that they tested, they trained it on. And the second kind of version of the experiment is one where there are doors that are open, and they can open and close. And during test time, some of these doors are always going to be closed, and then not during training time, some of the doors are always going to be closed, and during test time, they're going to be open. And you see how, in the same way, this agent kind of can perform, because of the way that it can perform this vector-based navigation. It performs much better than the other two baselines. So you can see that this one is like I believe is a DeepMind lab environment. So it has it's also a visual part to it, visual inputs. And here there are some other kind of mazes in which they show that during training, for instance, in this 2AB, this environment, during training, for instance, the agent was never given the possibility of going through these corridors. They were always closed, and but he found the agent through this door, and when at a test time, here was not trained, but like it was given the door were now open, it immediately finds it. It finds the shortcut, and this is only possible because it has this vector, this grid cell-like vector, on which it can perform this kind of calculations, and it knows that going in this direction is going to get closer and closer to the because it has the vector of how we call it, grid code, the grid code of the goal. Then it knows that going through this direction is going to get to the goal. It's going in the direction of the goal. It's getting closer. So this was like the paper. Was my summary of the paper, and thank you for watching.